Medical simulation, this one here. There we go, modeling simulation, now I found it. And so the first person that is going to present this afternoon is Hanin Hamdan. Did I
Next to you.
Oh. Excellent. You need to help these old guys like me to keep track of things like this. And she's going to talk to us about the body cooling vest for improving endurance under hot environment. And she looks like, are you a graduate student? Okay, you're a graduate student. If you look in the program, you'll see some of the people that are collaborating on this work, and I assume this is some of the work you're working on for your thesis. So, we're waiting for it. We have to get close.
Good morning, everyone. Today I'm going to present a model for a body cooling vest to improve endurance under hot environment. So let me just state the problem. Under hot environments, the body core temperature will increase above 37 degrees Celsius, which is the normal temperature. Therefore, the body will overheat. So in order to dissipate this excess heat, the blood will be diverted to the skin rather than to the muscles, and this will lower the productivity of the worker. Moreover, the workers may be subjected to heat-related illnesses such as dizziness, fainting, or maybe heat stroke. So in order to improve the endurance of the workers under hot environments, passive cooling vests may be used. There are different types of these vests. The first one is a convective garment, and it contains a blower fan to force the air in the microclimate region. However, these types of garments have high power consumption and low cooling capacity. The other type of garment is the circulating liquid garment, and also it has a pump, and the pump will force the cold liquid to circulate in capillary tubes that are placed inside the vest. However, these kinds of vests are heavy. The last type is the cooling vests that have phase change material. These materials will try to absorb the heat from the microclimate air, which is near the body, by changing the phase. So ice may be used, and also other phase change materials such as paraffins or mixture of salts. However, experiments have shown that ice is inefficient because of the very low melting temperature, 0 for example, and this will cause cold bites, thus discomfort. So salt PCMs are superior. These salt PCMs, they could be either incorporated as microcapsules inside the fabric, or they could be placed in packets, in small packets. But the microencapsulation wasn't very successful because of the volume and heat capacity constraint. So in this work, we will focus on the PCMs that are placed inside packets, and these packets will be placed in pockets in the cooling vest. So I'll start by giving some of the previous work, and then I will present the developed fabric PCM model, this mathematical model, and then the predicted results will be validated by experiments. So let me start by the literature review. I have to say that many of the work done was related to experiments that were performed on either thermal mannequins or human subjects. For example, an experiment done on thermal mannequins showed that the cooling effect of the vest depended on the temperature difference between the surface temperature of the mannequin and between the melting temperature of the PCM. Experiments on human subjects showed that the thermal stress was reduced when only the upper trunk of the body was covered and not the whole trunk, covered by the phase change material. Also, an experiment done by Zhao et al. Showed that the cooling vest was effective only in hot, humid environment, because in hot, dry environment, the evaporative cooling is sufficient to dissipate the excess heat. Now, regarding numerical modeling, few studies were done. For example, Ethan et al. Developed a mathematical model for the vest, and he used the enthalpy balance to predict the inner surface temperature of the PCM. Also, a numerical study was performed by Riley et al. And they performed a numerical model to investigate the transient effect of microencapsulated PCM fabric. So therefore, we can see that almost all of the work done focused on empirical methods, and few models exist. And these models did not study the flow characteristics of the air surrounding the PCM packets, and did not consider non-uniform PCM properties distributed in the vessel. So the main objective of this work is to provide a mathematical model that will accurately predict the temperature of air layers surrounding non-uniform PCM packets. So basically, I will state this mathematical model, and then I will validate this model by experiment. Now let's start with the model. This figure shows the two schematics of the side view. This is the first one, and the front view of the cooling vest. From the first figure, we can see that the worker is assumed to wear a fabric near the skin. This denoted by the inner fabric. It is important to not let the PCMs be in direct contact with the skin. And then there's a thin air layer. Then the PCMs, the non-uniform PCMs, are distributed. And then there's the outer fabric, but there's also another air layer separating the PCMs from the outer fabric. So I have to state the micro, or the air layers present here. First of all, we have the macroclimate air, and this air layer is trapped behind the outer fabric and between the PCMs. And then we have the microclimate air regions, and each region will be trapped between each PCM and the inner fabric. So this is a transit model of heat and mass transport through the cooling vest containing non-uniform PCMs. The inner fabric, the outer fabric, and the PCMs will be modeled each one as lumped system. Also, the macroclimate air will be modeled as lumped, but let me repeat, the macroclimate is the region behind the outer fabric and the PCM, and also between the PCMs. Now, also regarding the regions of the microclimate air that are trapped between each PCM and the outer fabric, each one will be modeled also as lumped, and but each region will have its own conditions, and this depends on the parameters of the PCM close to it. For example, its melting temperature or size or anything. Now, throughout the simulation, the skin temperature will be at constant value. Also, the ambient temperature will be constant. And initially, the temperature of the different air layers will be equal to the ambient conditions. Also, the PCMs are supposed to be at a solid state at first. So, the mass and energy balance equations will be written for the fabric layers, for the macroclimate air, and for each microclimate air region. And finally, of course, the equations will be written for the PCM and the solid, liquid, and the melting phase. Now, starting with the inner fabric, the first equation is the mass equation. The regain of the fabric, which is RIF, will be calculated at each time step. The regain means the mass of water vapor per the mass of the dry fabric. And the change of the regain will depend on the vapor pressure difference between vapor pressure difference of the inner fabric and the surrounding medium. So the medium surrounding the inner fabric are the skin, the macroclimate air, and the different microclimate air regions. Also, the variation of the regain will depend on the evaporative resistance of the fabric, and this is a characteristic of the fabric. And this resistance for the moisture transport. So we are taking it to be low in order to facilitate the moisture transport throughout the layers. The second equation is the energy equation, where the temperature of the inner fabric will be calculated at each time step. It will depend, of course, on the temperature difference of the inner fabric and the surrounding medium, as I said before, and it will also depend on the dry resistance of the fabric. The same goes for the outer fabric. The mass and energy equations will be written. But here, the medium affecting the outer fabrics are the environment and the macroclimate air. Now, regarding the PCMs, The PCM will be either at a single phase, if it's solid or liquid, or in its melting phase. So each time its temperature will be tested. If it's not equal to the melting phase, meaning that it is not melting. Okay, so its temperature will be calculated at the second time step, and the change in temperature will depend on its capacitance. However, when the temperature of the PCM equal to the melting, meaning that we are in the melting phase, so the melted portion of the PCM will be calculated, which is alpha. So alpha is the ratio of the melted PCM to the melted PCM. So it's basically between 0 and 1. At the beginning it will be 0, and as it reaches 1, meaning it means that all the PCM has melted. And this will depend on the HSF, which is the latent heat of fusion of this PCM. Now regarding modeling the airflow inside the cooling vest, we can see that the gap between the PCM packet and the inner fabric is supposed, or is taken to be small, and there's supposed that an airflow will be triggered by buoyancy forces due to the temperature difference between the macro and the microclimate air. And because the gap is small, this airflow will follow the Poiseuille regime. And this is the equation to calculate m dot, which is the mass flow rate of the driven air. So I have to denote that d is the distance between the PCM and the inner fabric, but w is the width. So these are the equations of the microclimate air. The first equation, the humidity ratio will be calculated at each time step. Of course, it will depend on the vapor pressure difference. And the second one is the temperature equation. The same goes for the macroclimate air. So therefore, these equations that will be written and will be solved using Euler equation, Euler forward method, and then after modeling, we have to validate our predictions. Therefore, in order to validate the model predictions of the long temperature of the microclimate air and the macro, experiments will be done during the melting phase. So transient temperature measurements will be taken for the two air layers on a cylinder PCM system. Experiments will be done on a heated cylinder. It will be kept, it is controlled, and it will be kept at steady state, steady temperature, which is 35. And this heated cylinder will be placed in a chamber, also a controlled chamber at 28 degrees. The PCM packet used, it is a commercially available one. It's made up of Goldberg salt with a melting temperature of 28 degrees. These are, so for example, the latent heat of fusion is 126 kilojoule per kilogram. The specific heat is 3.6 kilojoule per kilogram Kelvin, and its density is 1.45 kilogram per meter cube. So this is a schematic of the experiment. We can see this is the heated cylinder, and I've used the three metallic cages, an outer metallic cage in order to hold the outer fabric, and the other two cages in order to squeeze the PCM. So by this configuration, we can see that the PCM is trapped between the macroclimate air layers and the microclimate air one, and this is what the model assumes. This is the PCM that I've used. It's 13 centimeter by 7 and 1 centimeter in width. So this packet was kept to solidify all night at 20 degrees, and then the heated cylinder was kept for 10 minutes to reach the steady state temperature, which is 35 degrees. And at the onset of the experiment, the initial temperature of the PCM was recorded to be at 21. And then these temperatures, the temperature of the air layers, were sampled at 10 readings per second and are averaged and recorded every 60 seconds with accuracy of 0.1 degree. So these are the results. This is the result of the microclimate air temperature. I have to denote that in this modeling we have only one microclimate temperature, microclimate layer, because we have one PCM. So this is the result. We can see that there's a good agreement between both the predicted values from the model and the experimental results, with a maximum error of 4.5%. And the second figure shows the macroclimate temperature for the predicted and the experimental results, and there's a good agreement between both, and with a maximum error of 2.5%. So to conclude, today I presented a mathematical model for this vest, and this model simulates heat and mass transport through a vest containing non-uniform PCM packets, and the model predictions showed good agreement with the experimental results. Thank you.
Do we have any questions?
Yes. What would be the expected weight of such a weight?
It could be 2 kilograms, but we are working on optimizing the cooling vest.
And any idea about the expected cost?
Expected cost. They are commercially available if you want to buy a cooling vest. It's around $400, but it's not the optimized one.
Exactly, if they are commercially available, what's the purpose of your study?
All the available PCMs, the cooling vests, they are not optimized. They have high weight. So the idea behind this work is to try to optimize. Yes, I know. In this model, the PCMs are non-uniform. So this will give the advantage of trying to change, so for example, lower the weight on the lower torso, just focus on the upper part. So this will reduce the weight of the cooling vest.
Other questions? Okay, thank you.
Thank you.
All right.
So next, it's on now. Next up is Nagham Ishmael. And Nagham is going to talk to us about predicting ventilation rates of clothed human segment.
Good afternoon. Thank you for presenting me. Clothing insulation and ventilation rates are parameters that affect the heat and mass transfer properties, and then heat and moisture comfort. Both of these parameters are impacted by fabric properties, garment size, garment design, body postures, and environmental conditions. Researchers agree that wind conditions and garment design or apertures are the most important parameters that affect ventilation. Noting that the ventilation is essential because it can dissipate heat from the human body and then prevent heat stress. That's why I would like to present today the effect of apertures on ventilation rates and heat loss from closed heated cylinder in crosswind. During my presentation, I will go through these points to come up with an integrated mixed convection heat transfer model of closed human body subject to external wind. First, let's start with some literature review. Comfort indices are based on static ensemble clothing insulation, and they assume a sedentary activity level at low air velocities. However, to consume less energy, researchers have focused on increasing wind velocity to bring thermal comfort at elevated air temperature. Now, research in local clothing ventilation took two tracks. One was empirical, which deals with the whole ensemble ventilation and does not consider segmental ventilation. And the other is by modeling, which has advantages in studying the effect of permeability, garment apertures, and wind conditions for predicting segmental and overall ventilation rates, and the wide applicability to incorporate with a bioheat model that did use the core and skin temperature. Now, clothing microclimate ventilation is essentially related to the flow characteristic in the microclimate air layer. The microclimate air layer is a layer trapped between the skin and the fabric. It's also related to the clothing permeability and to the open apertures. The flow characteristics of this air layer is related to two phenomena. The first, convection induced by wind conditions and by the opening that drive the flow upward, driven by the pressure difference, and the natural convection, which is affected by the warm body effect and the sweat at the skin. Now, previous research on modeling the body as segments focused mainly on open-top cylinder that represents the human trunk, the closed human trunk with wide opening at the neck, and they use a correlation to calculate the ventilation at the limbs. The study of the heat losses and ventilation rates of the whole human body used usually resistance model integrated with the bioheat model. Thus, the literature does not have the effect of mixed convection on open bottom closed cylinder, which represent the major closed segment of a human body. Mixed convection means natural and forced convection. Now, in order to estimate the ventilation of the human body through clothing, the closed human body is divided into 5 segments: 2 arms, 2 legs, and 1 trunk. This figure shows the physical configuration of the closed human segment. It consists of 2 concentric cylinders, one for the skin and the other for the fabric. The microclimate air layer is trapped between these 2 cylinders. This configuration is placed at wind conditions V infinity. Now, for this case, the opening is from the bottom, so it models the limbs. This opening drives the air to be lifted upward because of pressure difference and because of natural convection. Because the thickness of this air layer is very small compared to L and to R, the radius of the cylinder, we can open this annulus and move from an annulus cylinder to 2 parallel plates where the microclimate air layer is modeled. So we can apply the plane Poiseuille flow between these 2 parallel plates in the axial direction and in the angular direction. So because of this small thickness, the negligible variation of pressure and temperature in the radial direction are considered, and the fully developed mixed buoyant upward flow, and a transformation from 3D to 2D problem. Regarding the fabric, a 3-nodes model is used. It consists of the outer fabric, the inner fabric, and the air void node. The outer fabric is the exposed exposed surface of the yarns, which is in direct contact with the air in the void node, while the inner fabric is the inner portion of the yarns and it is surrounded by the outer fabric. Regarding the mathematical formulation, we will start with the mass conservation. M dot leaving minus M dot entering is equal to 0. Thus, the variation of the axial mass flow rate and the variation of the angular mass flow rate will be equal to the mass flow rate entering through fabric. The penetrating mass flow rate is related to the pressure difference between the microclimate air layer and to the surface and the surface pressure or the adjacent air layer. Because we have applied the plane Poiseuille flow in the angular direction, we can substitute the variation of the angular mass flow rate by a term that's proportional to the pressure difference across the theta direction. The same for the axial mass flow rate, except that the axial mass flow rate will take also into account the natural convection, which is related to the pressure to the temperature difference between the microclimate air layer temperature and the void temperature. So this is called the pressure equation. By applying the energy conservation to the air, to the microclimate air layer, which is the sum of the convection term, conduction term, and heat transported by the mass flow rate. Noting that the maximum is used here because we don't know if the penetrating mass flow rate is from the microclimate air layer to the ambient conditions or vice versa, depending on the pressure difference. The energy conservation is also applied to the fabric void node and to the fabric outer node. All the convection terms are taken from published papers that aim to give them experimentally. Now, the associated boundary conditions for the airflow are summarized as: we can use the mass flow rate from Bernoulli at the opening that where the flow is driven upward, and then it's zero at closed end because there's no mass flow rate, the top is closed. Now, because of the symmetry line, the mass flow rate, the angular mass flow rate is zero at theta equals 0 and theta equal pi. Now, zero temperature gradient when the air is leaving, and the temperature is ambient at the inlet flow. Of interest is to define the microclimate ventilation rate as the positive mass flow rate penetrating through fabric. The heat loss from the skin to the microclimate air layer is the sum of the convection and the radiation from T-skin. Now, after writing the pressure equation and the energy equation, we will discretize them using the finite volume methodology, where the pressure and temperature are discretized using the central differencing. And from the pressure equation, we will get the pressure of the microclimate air layer, assuming that the temperatures are constant, and by assuming them. And then we will get the temperature from the energy equation after calculating the pressure. Another time we will get the temperature and then recalculate the pressure. These iterations will be repeated until convergence of temperature and pressure. The convergence took 300 iterations and about 30 seconds for each segment. Now, in order to validate our model, we have done an experiment on a wind tunnel where the closed cylinder is installed inside. This cylinder is formed by two concentric cylinders. The inner cylinder is from copper, and inside it we inserted a rod to maintain a temperature constant, which is the skin temperature of 34 degrees Celsius. The outer cylinder is sheeted by fabric of permeability 0.05 meter per second. 7 thermocouples are mounted in the microclimate air layer between these two cylinders, and at each time we will rotate the cylinder to measure the variation of temperature angularly. The wind speed was 1 meter per second, and the ambient temperature was 25 degrees Celsius. This section focuses on the validation of the modeling by experiment. As we noted that the temperature is varying axially, it is increasing because it's entering from the ambient conditions, and it's increasing because of the high pressure at the top. Good agreement was found between experiment and modeling, as well for the average temperature versus the angular direction. To further emphasize about the importance of the opening at the bottom, we have analyzed our simulation using three cases. One where the opening is from the top, representing the closed trunk, and one for the opening at the bottom, representing limbs, and one where the top and the bottom are closed. As we noted that the open top, in the case of the open top cylinder, the temperature decreases. In fact, In fact, the temperature is high at the bottom because of this closed end, and it's decreasing because of the ambient temperature, ambient mass flow rate that are entering through fabric. Now, regarding the case of the up and bottom temperature, the inlet flow was at ambient temperature, and the temperature is increasing because of the closed end at the top. For the closed end cylinder, the temperature is slightly increased because of natural convection. The mass flow rate penetrating through fabric is related to the pressure difference, and thus we will notice that it is higher in the case of the up and bottom cylinder. This table will show us the heat losses and the ventilation rates in 3 cases. So as we noticed that the opening from the bottom enhances the ventilation and allows more air to penetrate through fabric. To conclude, a new mathematical model derived from the first principles is proposed to present the coupled ventilation and heat convection in a vertical open bottom and an annulus between concentric fabric cylinder and heated solid cylinder placed in perpendicular to airflow representing the closed limb. When subjected to uniform crosswind, the open bottom cylinder presents significant ventilation rate when compared to open top and closed end cylinder. The reason is that the open bottom end allows the ambient air to be sucked and then to ventilate the heated cylinder representing the skin. Thank you.
Any questions for the presenter?
Why didn't you and Hanin combine your projects in creating one supersuit, for instance?
Yes, you are right, but Hanin used a model where there's no flow, there's no induced flow by wind conditions. It's only natural convection, but the next step can be this.
That was actually my question. You have one closed cylinder, so how are you going to integrate this whole thing for the full human body?
Now I'm modeling the human body with connected segments, so I will connect all these segments to study the ventilation through the whole human body. And I incorporate also the mass transfer to be more real and accurate. And then I can apply this model, for example, to find the ventilation through protective clothing, because wearing protective clothing is an issue that can increase the metabolic rate and can induce a heat stress on the wearers.
Other questions? Okay, well, thank you. Okay, and next up is Ayad Faisal. I hope it's called Faisal. All right, I'll get it. And he's going to talk to us about a new full-scale multi-physics model to predict hydrodynamics and heat and mass transfer performance of a water-cooled evaporator. Thank you.
Sorry.
There.
Good morning, everyone. So the title of our presentation for today is a new full-scale multi-physics model to predict hydrodynamics and heat and mass transfer performance of a water-cooled evaporator. So the first question actually, why do we really need to build a full-scale model for a specific application, in particular here the evaporator compartment, which is capable to capture every single detail in the unit without including any drag or some sort of lumped analytical approaches. The answer to this actually is straightforward. That as we know that in buildings, residentials or commercial buildings, we still rely on installing edge VAC systems. And of course, in addition to the improvements done at the building envelope, for example, by installing special type of insulators to save energy, or by, for example, incorporating lobby windows, this all helps in saving energy. However, we're still paying a bill, and this bill comes from the operation of our equipment. And one of these, among these equipments, is the HVAC system installed in the building. So we have to take a look at this system. So if we are able to, of course, improve the efficiency or the performance of our unit, we will be also saving energy. However, in this presentation, I will not mention anything about the optimization of the equipment, but rather to state the importance of building a numerical model of a specific application. For example, here we took the evaporator compartment. So here just you see here some facts and figures. For example, as you see, coolers, air conditioners, or refrigerators share about 50% in electricity consumption. Another source showing that space, cooling, and heating constitute about 40% from the energy used in residential and about 30% in commercial buildings. So there is always a need in the last figure to improve the COP of our application, the HVAC system in this case. So as a summary of the strategy that could be considered to save energy, the triple R equality. So we can either recycle energy, this is a way to save energy. Reusing energy through, for example, cogeneration process is also a way to save energy, or reducing energy equivalent to, say, improving the efficiency of the unit. This means we can reduce energy. So these three allows us to save energy. Of course, our future target is to improve the efficiency of a specific application. But as I've mentioned, I will not talk about optimization, but rather present a numerical model of the evaporator compartment. Now the next question is, who is our target in this case? This project actually targets air conditioning manufacturers. So if we are able to come up with a reliable and robust model which is capable to predict every single detail without including any drag or lumped approaches, this will actually allow air conditioning manufacturers to improve the design and efficiency of their AC units through building, for example, a full-scale mathematical model which will give better and more advanced opportunity to analyze and investigate the performance before putting into production, before putting the unit into production. How this is done? By building a numerical experiment. I mean by this term, to build a model which actually reflects what's happening on the site. So, for instance, here the application that we have done, we start by the geometry of the unit. We then move to generating the numerical model, and through computer simulation we can define our inputs and set up, run the simulation, and finally obtain, we can visualize the details in the last figure as you see. So here we're using CFD codes in order to achieve this purpose. And why using CFD? The advantage of this, because we can reduce much of experimental costs. Why? Because we can only have one concept built experimentally, and we can validate it by a CFD code, and we can modify from the computer model the parameters without each time building a new concept and running the experiment. This will add much higher experimental cost. So through computer technology or power, we can achieve this numerically. Another advantage of using CFD is computation fluid dynamics for those who is the ability to visualize and access more details compared to an experimental experiment. How, for example, if we need to access a location, we need to sometimes use probes, and sometimes experimentally it could be difficult. Or if we are able to use probes to extract certain information, sometimes many installed probes could deform the flow and could sometimes shift from the reality. So if we have a numerical model, we can actually reflect what's happening experimental, and this is what we are forward towards to. However, CFD has some disadvantages. One of it is high computational cost, especially for complex type problems. However, a second disadvantage is the pre-processing tools, which is the measure used in order to generate the control volumes. Actually, sometimes could be tough for complex type applications. However, these two disadvantages actually are resolved or has been resolved by the, of course, advancements in computer power. So we have now high-speed computers and with high memory. So we eliminate the first disadvantage. The second one, also we have a lot of improvements in the machine process. So we can now, even for complex type application, generate millions of points with a couple of hours. So using CFD actually is advantages compared to its disadvantage. So here, of course, get the facts before you manufacture. Now I will start presenting the modeling procedure of the application that we have done. So first of all, this is our physical model. It's just a coil plugged inside this box where air enters from the two inlets, hit the coil and leave the outlet, exchange it and leave the outlet. Okay, so our coil here is made up of 600 fins, 84 pipes arranged in staggered manner, and the table below and the figure shows also some geometric specifications we're not interested in. Okay, the second step, after we have the geometry, we come up to generate the numerical model, and here we need to generate small control, decompose the geometry into small control volumes. And in this application, we reached generating up to 30 million control volumes, and an additional conformal mesh was generated at the solid fluid interfaces to assure or guarantee continuity in heat fluxes. So here we have two fluids and a solid region separating the two fluids. Next step is we need to identify our variables we're solving for what. So we come with a mathematical model. So here the problem actually is complex by nature and involves solving for flow by the four equations: continuity and free momentum, temperature, turbulent quantities, species, and two volume fraction equations. So we have 10 partial differential equations to be solved for this problem. So as a rough estimate, in order to know the size of the array required to store these variables, we have 30 million control volumes, and each control volume is an unknown. So times 10 variables, so we need an array of size about 300 million. So it requires some memory. The concept actually is based, we're here solving a conjugate heat transfer problem. Why? Because we have an interaction between two fluids. The air is crossing the coil and the refrigerant inside the coil, so the solid region separating the fluid. So this is a conjugate heat transfer problem, and it's also a multi-phase heat conjugate heat transfer. Why multi-phase? Because we're accounting for condensation at the surface of the coil. So here the concept starts by defining three phases. One primary phase containing the humid air mixture, and two secondary phases containing the water condensate, because we're collecting a condensation water condensed at the evaporator surface, and the secondary phase is the refrigerant. In this case, it's liquid water flowing inside the pipes of the coil. Here, the humid air mixture, of course, is made up of dry air plus the water vapor species. For those who would like to know which equation we are solving inside Fluent, there's a CFD commercial code. We have the continuity, we are using the mixture model for the multi-phase. We have one continuity and three momentum equations for the flow. Temperature by the energy equation. Water vapor are predicted by the species equation. Two volume fraction equations for the water condensate and the refrigerant. And of course, due to the turbulence effects, we need to account for these through turbulence model. We're using the realizable capsule model. Now remember that we're accounting for the condensation happening at the coil surface, so we need to model these effects. Here we used fixed law in order to compute the condensation rate and accordingly the latent heat release. However, to do so, we have to modify in the CFD code through building some user-defined functions, and here is an integrated C code that we have developed in order to modify these three sources that you see in the energy equation, species, and the volume fraction equation. Now, after we have the geometry, the numerical mesh, we define our variables. We need to know the model inputs to closed system equation. These are the boundary conditions. We have the air zone, of course, boundary conditions for the air zone, and one for the refrigerant zone. I will not go into every number here, but I just mentioned we have the air flowing from these two inlets at a velocity of 3.99 meter per second with temperature 300 degrees Kelvin, and it contains 0.0111 kilogram per kilogram air of moisture, water vapor. Refrigerant is flowing at 0.323 meter per second at 279 degrees Kelvin. Just the other walls of the unit, of course, are modeled with no slip conditions. That is, the velocity is zero at the walls, and they are insulated. And remember, between the two fluids, we have the solid region, which is made of fins and pipes. In this case, the pipes are made of copper and the fins of aluminium. So now, once we have identified all these inputs, we run our solution. We hope it will converge. And then we post-process our results. Here, the post-processing, you can have many options, either by defining several probes points or measuring planes in order to visualize how the flow is changing and the flow parameters, properties, temperature, species distribution, etc. So here the gray plane shown in gray color, as you see, we're used to numerically measure some flow properties. I will not go here into deep analysis of the results, but just going straight forward. Here, for example, here, look at the air flow direction in this black arrow. The first figure shows a plane before the coil and the planes after the coil. And there you see the distribution of temperature, the change of temperature, of course, due to the heat transfer happening. This is known. The second figure shows the spatial distribution, axial spatial distribution of humidity ratio. And here, as you see, the model what predicted the loss in humidity content inside there due to the condensation happening. So, but here you notice non-uniform distribution of the humidity ratio as you move axially in this direction. And actually, this is because we have the coil temperature in this case is not uniform. We have refrigerant entering in this direction at a certain temperature and air crossing like this. So we will have change in temperature. So the dew point temperature will change, and accordingly we'll predict non-uniform condensation rates. And this appears here in these illustrated in the second row of figures. The last row of figures show the velocity magnitude contours also as air crosses in the axial direction. So anyway, you can visualize any property it's of interest to you. You can analyze it. Here, for example, I used planes, XY planes at different Z directions, and you can also look at the flow vectors colored by, for example, temperature. So you can look how the velocity changes with temperature, for example. Monitor both properties, and you can rely on 3D, of course, to see, for example, you can inject some path lines to see how the properties, velocity, temperature changes. Here, for example, you see some recirculations at the extremities of the coil, so you might have opportunity to eliminate these maybe through modifying geometry of the coil. So once you have this information, it will be important. The last figure here shows the refrigerant zone streamlines. Here, remember the pipes pass, the refrigerant pass through the pipes, and also we have non-uniform outlet temperature distribution for each row. And this, of course, obvious. At the first row, we will have higher temperature gradient because the heat transfer will be higher, still the air is hotter and the refrigerant is cold. And as air crosses this coil, its temperature has decreased, and therefore the heat transfer in the second row of refrigerant will decrease. And here is predicted in the last figure, now the airflow direction is from right to left. So you notice the temperature gradient decreases as you move gradually in the refrigerant rows. The last figure shows distribution of humidity and temperature. Again, this is, I mentioned before this, the non-uniform distribution due to the non-uniform temperature distribution of the coil surface, and accordingly you can see the variations in the humidity ratio contours. Here, just I'm showing the importance of using CFD in order to model any application, any complex application. And this, of course, we will not stop there. It could be we use this. We we will hopefully use this to optimize later on, for example, playing with the model parameters, geometry, etc., to improve the performance or capacity. Here in this project, in this presentation, I'm showing you only two sets of results, one for a dry coil and one for a wet coil. Predicted capacity was 27 watts for the dry, 28,724, so it's higher for the wet coil. That's why wet coil assumptions are give higher capacity compared to a dry coil one. And of course, we tried to validate the method with available experimental data with similar coil construction, the one in the paper of Professor Fadl. And we also developed like an analytical approach based on the NTU, modified approach, in order to see where we are with respect to this. And here you notice the 4% difference, for example, predicted by the CFD and analytical. And this difference actually could sometimes be higher. And this is the limitations of following analytic. In some cases they are beneficial. However, if you need to go more into the reality, we have to rely on CFD to get more details. So as a conclusion here, we have built a full-scale multi-physics CFD model in order to model the multi-phase conjugate heat transfer in the evaporator compartment in this application. We presented two sets of results, one for a dry coil assumption and one for a wet coil assumptions. And this research aims to aid manufacturers in improving the design of HVAC units by building numerical experiments capable of exploring a lot of details of the features of thermal and flow fields. So get the facts before you manufacture. Thank you for your I would like to thank also my advisor, Professor Fadl, for giving the opportunity to adventure through this project. So thank you for
The questions? Pretty comprehensive presentation.
Sorry, what was the parameters you added in the equation? You showed a set of equations and you added
yes,
a few
the
parameters.
CFD code, we're using a flow, but sometimes it lacks some abilities to modify. For example, we're accounting for condensation. So we need to account this. You're saying about this.
Okay.
This. And you need to build a code in order to modify the source terms. And
Okay, excellent, good job. And I think that concludes this session, yes?
Yeah. I'd like to say that we're going to have open lunch at the terrace here under the sun, and it's an open buffet, so everybody is invited.
We normally should start at 3 o'clock. So, first we will have a presentation of about heating water using the recovered waste heat from boilers in HVAC applications, thermal modeling and parametric analysis. And Mahmoud Khaled, who is a PhD, who is one of the authors of this paper, and all these authors are faculty members in the mechanical department of the School of Engineering of the Lebanese International University. I would like, before giving him the floor, just to tell you that, of course, we'll have about 1 hour and a half for 3 presentations. So after each presentation, we will have some time for questions dedicated to the presentation, and we'll see if at the end we have some time for general questions, because some of the papers are related to each other, and perhaps it will be fine to have a general debate afterwards. So, Mahmoud, you have the floor.
Okay, thank you for introducing our work. Hello, everybody. I'm pleased to be here today to present you our work as the Energy and Thermal Fluid Group of the Lebanese International University, entitled Heating Water Using the Recovered Heat from Boilers in HVAC Applications, Thermal Modeling and Parametric Analysis. My presentation will be outlined as follows. I will be introducing the work with some lights on heat recovery magnitudes and importance. Then two thermal modeling and iterative procedures of the code used for the calculations, results of the calculations and corresponding analysis, and finally conclusions. First, first introduction. As most of you may know, the actual world tendency is toward reducing fuel consumption and at the same time reduction of carbon dioxide emission. This can be mainly accomplished by renewable energy like wind, solar, geothermal, wave, biomass, and at the same time energy management, energy saving or energy efficiency, where energy recovery or heat recovery is a main axis of this domain, which is taking a big importance nowadays, where it is defined as the capture of energy lost in applications such as internal combustion engines, HVAC, heating, ventilating and air conditioning, chimneys, generators, etc., and use them in useful form, and otherwise will be lost. To give some illustrations on importance of energy recovery or heat recovery, the following diagram shows the energy balance or typical magnitude of energy balance for a generator, where the input energy of burning fuel is divided between different components like exhaust gas, engine cooling system, etc. One can shed light on the 36.5% of exhaust gas energy rate or heat, where, for example, the waste heat from exhaust gas of a 30 kVA input energy generator can drive a 11 kVA generator. Another example, if we look at internal combustion engines, the input energy of internal combustion engines is usually almost equally distributed between three components: the exhaust gas of the vehicle, the cooling system, and the brake power, the useful power. In this context, the exhaust gas or the energy lost in the exhaust gas of a 600 horsepower Porsche Turbo 911 can drive two BMW 3 Series. Always in the same context, if we look at boilers used in the HVAC applications, boilers are equipments that mainly function on burning fuel in order to provide 70 to 80% of heat, cold heating load to the occupied space, and 10 to 20% of exhaust gas to be lost in the atmosphere. If we look at the 20%, and in the same context, the exhaust gas of a boiler of 200 kilowatt can drive another boiler or burn or provide the energy to another boiler of 40 kilowatt. So in this context, the present work concerns water heating using the recovered heat from boilers and HVAC applications. To proceed, a thermal modeling and associated code were developed, and calculations or parametric analysis were achieved. The heat exchanger considered in the work was concentric tube heat exchangers. I will be now describing somehow briefly the thermal modeling and iterative procedures of the code used. Mainly the iterative procedures of the code is based on two set of governing equations. First set concerning the exchanger size, and other set of governing equations concerning or related to the boiler side. If we look at the exchanger side, the basic energy equation is relating the energy gained or the energy rate of energy gained by water equals the energy rate lost by the exhaust gas, and at the same time equal to the heat rate exchange between the two fluid streams. If we look at the right member of the equation, UA delta T logarithmic, which is the heat rate exchange between the two fluid streams, this term is mainly governed by three terms. A, where A is a heat transfer area, U, the overall heat transfer coefficient, which comprises mainly the convection of water with the inner or with the wall of the heat exchanger, conduction in the wall of the heat exchanger, and convection in the exhaust gas of the exchanger, and delta T logarithmic, which is a logarithmic temperature difference, mainly function of the inlet and outlet temperatures of water and gas. Manipulating the different equations yield to the following difficult relation where the only unknown is the outlet temperature of water from the recovery system. This equation cannot be solved analytically. It should be done by iteration, and at the same time, in order to take into account the effect of temperature on thermophysical properties of the system of the fluids, which are mainly the specific heat Cp and the viscosity, conductivity, etc., which are implicitly included in the overall heat transfer coefficient U, which I reiterate that it's mainly function of the two heat transfer coefficient of convective coefficient of water flow and gas flow. If we look at the boiler side, usually boilers are functioning, or boilers are governed by many efficiencies. The overall efficiency of a boiler is the ratio between the useful heat or the heating load of the space divided by the input energy of combustion. At the same time, the lost energy in the exhaust is the difference between the input energy and the heating load of the space. Combining the two equations, we can find a relation between the energy lost in the exhaust, the heating load of the space, and the overall efficiency of the boiler. On the other hand, the mass rate of fuel can be calculated from the input energy of combustion and QC, which is the heat of combustion of the fuel of the boilers, mainly diesel, which help us to relate the mass flow rate of fuel to the space heating load, Q dot heating, the heat of combustion QC, and the overall efficiency of the boiler eta B. This yield finally to the mass flow rate of the gas of the exhaust gas of the boiler, m dot G, which is A plus 1 m dot F, with A or AF, the air to fuel ratio of combustion. Now, if we look at the first law of thermodynamics in the energy lost in the exhaust, we can relate the energy loss in the exhaust to the mass flow rate at gas and the temperature difference. With the mass flow rate of gas already calculated, we can calculate the two main parameters which are input parameters to the first set of governing equations, the mass flow rate of fuel and the input or the inlet temperature of gas to the heat exchanger, or the temperature of exhaust gas. Finally, in the iterative procedures to summarize, the thermal modeling or code, or the two set of governing equations, has a set of input parameters like geometric parameters, the inner diameter and outer diameter of the exchanger, the length L, the mass flow rate of water, inlet temperature of water, the heating load of the boiler, the efficiency, air to fuel ratio, ambient temperature, and heat of combustion of the fuel. And the main output is one of the output temperatures, since they are related as you have shown in the exchanger side calculations. And finally, we can calculate the main output P exchanger, which is the thermal performance of the exchanger, and which is energy recovered from the exhaust gas of the boiler. Briefly, the concept of the iterative procedure of the code is described in the diagram of the right side, which start mainly by fixing the input parameters and using the second set presented of governing equations to calculate in the boiler side the exhaust gas flow rate and exhaust gas temperature, which is the inlet temperature of gas in the heat exchangers. Then, with the other set of input parameters, to solve by iteration, in other terms, iterating with respect to the outlet temperature of water by setting an initial temperature of water at the outlet and incrementing the outlet temperature in order to have the convergence where the first or left member and right member of this complex equations will be equal. Now, as results and analysis, first I will present the configurations tested. Indeed, there are 6 configurations corresponding to 2 geometries. As shown at the upper right, we have 2 geometry. A first geometry where the exhaust gas flow in the inner tube and outlet or cold water flow in the annulus of the concentric tube heat exchangers, and a second geometry of flow pattern tube where exhaust gas flow in the outer or in the annulus and cold water in the inner tube. For the 2 set of calculations that will be presented later, a concentric tube of 3 meter length is considered. The water inlet temperature is fixed at 20 degrees Celsius, average temperature. The heating load is considered equal to 100 kilowatt, which is a magnitude order for an apartment of 5 to 8 people. The ambient temperature is set at 20 degrees Celsius and air to fuel ratio to 15, which is almost approximately stoichiometric combustion. And in each geometry, 3 configurations were tested. First geometry, the inlet diameter were fixed and the outer diameter varied from a ratio of 1.25 to a 1.75. For the second geometry, the outer diameter were fixed, which correspond in real application to the diameter of the exhaust pipe of the boiler, and the inner diameter is varied from 25% to 75% for 3 configurations. The first set of calculations were done by varying the flow rate or the water flow rate from 0.02 to 0.5 kilogram per second, which is a magnitude order or a range of flow rate encountered in water heating applications. And for the 3 first configurations, I repeat, the 3 first configurations correspond to the case where the exhaust gas flow in the inner tube and water in the annulus. And we have varied the outer diameter to have three diameter ratios, outer to inner diameter of 125, 1.5 and 175. Here in the two curves we show at the left the variation of the outlet temperature in function of the water flow rate for the 3 tested configurations, and at the right the variation of the heat rate or the thermal performance or the energy rate recovered. As you can see, the outlet temperature decreased exponentially with the water flow rate and at the same time decrease with the outer diameter. In other terms, by fixing the inner diameter and increasing the outer diameter, we decrease the amount of energy recovered from the exhaust gas. If we look or focus on the diagram of heat rate variation, we can show that for a outer to inner diameter of 1.75, the heat rate is almost constant, around 10 kilowatt, and we can see that we have two sudden changes in the curves of 1.25 and 1.75. These sudden changes occur approximately at 0.4 kilogram per second and 0.36 kilogram per second. Here is an attempt to explain the features of the trends shown in the heat rate variation. If we look at the Reynolds number of water, Reynolds number is a dimensionless form of the velocity of water, which many of you can know that it transduce or translate the nature of the flow between laminar or turbulent. If we look at the flow corresponding to an outer to inner diameter of 175, the Reynolds number is almost below 2300, which correspond to the transition from laminar to turbulent. This is why the heat rate for the case of 1.75 is almost constant. As we see at 0.36 and 0.4 kilogram per second, the water flow is transferred from laminar to turbulent. This is why sudden changes occur at 0.36 and 0.4 kilogram per second. Now for the second set of calculations, the same parameter or the same variation of the water flow rate was done, but this time for the three last configurations. This time the water flow in the inner tube and the exhaust gas in the annulus, with the outer diameter this time fixed and the inner diameter varied. We see this time that the outer diameter or the outlet temperature of water increase by increasing the inner diameter. And the inner diameter, when the inner diameter is the most close to the outer diameter, the heat exchange is enhanced. If we look at the heat rate, now we have the heat rate almost increasing, since as we may show now, from the beginning, when we increase the inner to outer diameter, the transition from laminar to turbulent flow occurs at lower range of water flow rate. If we look closely, we see that from 0.12 approximately kilogram per second, all flows or for all cases, the water flow rate become turbulent. To conclude, this work concerns a first baseline consisting on a thermal modeling and iterative procedure code to calculate or to give some recommendations on different geometrical configurations for recovering heat lost from boilers. A case of 100 kilowatt boiler or 340,000 BTU per hour were considered. It was shown that water temperature up to 100 degrees Celsius can be obtained depending on the mass flow rate. Two flow pattern or two geometry were tested, were for a first set of configurations the water flow in the annulus, and a second set of calculations were water flow in the inner tube. Configurations of geometry 2 show higher heat rates than configuration of geometry 1. In other terms, it is more recommended from a heat transfer point of view to flow the water in the inner tube. When geometry 1 is implemented, it is more recommended to have the outer diameter the most closely possible to the constant inner diameter, and when geometry 2 is under consideration, the inner diameter should be the most closely possible to the constant outer diameter. Effectively, there are a lot of future works in this domain. The main two important future works that I can notice. First is to have more parameters tested other than the geometry or the configuration of flow pattern and diameters, and second future work to test experimentally the concept suggested. Thank you for your attention. Question.
Thank you very much. So we have time for questions.
What would be the effect of cooling the exhaust gas on the gas itself?
Indeed, there is a minimum temperature limit for exhaust gas depending on the kilowatt of the boiler. But usually this limit we cannot be below 140 to 180 depending on the kilowatt of the boiler. Otherwise, we will have environmental effect.
Wouldn't you have problems in the condensation problems and in the exhaust process itself?
I think this may be tested.
Other questions? Well, if not, we will go through the second presentation, and afterwards you will have also the possibility to ask other questions because it is partly related. Okay, so thank you. The next presentation will be a review on HVAC heat recovery systems made by Mohammad Ramadan, who is also, as Mahmoud Khaled, assistant professor, PhD and assistant professor currently in the Department of Mechanical Engineering of the Lebanese International University of Beirut. So Mahmoud, you have the floor. I'm sorry. Mohammed, sorry.
Thank you. So hello everybody, my name is Mohammed Ramadan, and I'm an assistant professor at the Lebanese International University, so in the same team with Dr. Mahmoud Khaled. So my presentation will be almost in the same framework. So it will be about heat recovery systems, entitled A Review on HVAC Heat Recovery Systems. So the outline of my presentation, first I'll do a small introduction, followed by presenting the 3 different HVAC heat recovery systems. Finally, I present 2 applications and conclusion. So as you already know, today we are facing a severe energy crisis, which is due to several reasons: the reduction of fuel reserve, the high cost of fuel, and the dangerous level of pollution. So to face this crisis, several solutions were proposed, mainly in the renewable energy domain, such as solar energy, wind energy, and other types of renewable energy. However, there is another solution, which is energy recovery, that may be proposed to face this energy crisis. So the concept of energy recovery is to recover the lost energy that that may occur in any mechanical or engineering system. So if we have a mechanical or engineering system, of course we have some lost energy. So the idea of energy recovery is to use this, to recover this lost energy and to use it in another useful form. Of course, this energy may be kinematical, thermal, or other type of energy. Now the question is, where can we find lost energy? The answer is, in fact, if we take a look around us, we can find a lot of source of lost energy. Example, cars, generators, industries, and even in our houses, such as HVAC systems. So the aim of this presentation is to present a short review on different different types of heat recovery systems applied to HVAC systems. Before that, let's start by presenting what is an HVAC system. So an HVAC system, in brief, contains four main components, which are the compressor, the condenser, the expansion valve, and the evaporator. Of course, in the cycle, there will be some change, phase change, and pressure change depending on the component. So we are interested in or at the condenser, where generally the condenser evacuates or dissipates heat, and this heat is a lost heat, it's not utilized. So the idea is to recover this heat and to use it mainly to heat. We'll see two systems where this heat will be utilized to heat water. So let's start by the first concept of the first system. So we call that the immersed condenser heat recovery system. The idea is very simple. So instead of cooling the condenser using a fan, we will replace that by a water cooling system. That's to say, we'll use a water tank in which we'll immerse the condenser, so that the condenser will be cool and the heat dissipated by the condenser will heat the water. Of course, we can use a more sophisticated system on the same idea, where instead of using directly the heated water, we can use a storage tank and a pump, so that we can have a cycle. So from a cold tank, the water will cycle, and for some, and at certain conditions or criteria, the heated water will be stored in a tank. Now, if we do the balance sheet of this type of heat recovery system, we will find that we have two main advantages. The first one is that we have a high gain of temperature. The average is almost 25 degrees. And we don't need to use the fan anymore to cool the condenser. However, we have also two main drawbacks, which are that we need to modify our system to replace the air-cooled condenser by a water-cooled condenser. And of course, immersing the coil into water may damage the condenser. Now, the second type of heat recovery system is the air-to-water heat recovery system. Here, the idea is to keep the system, the HVAC system, as it is, and instead of changing the condenser or immersing it into water, what we'll do is to use the hot air, which is utilized to cool the condenser, and we'll use a heat exchanger in which will flow cold water, and the hot air will heat the cold water. So in this case, we don't need to modify our system, and this is one of the main advantage of this type of heat recovery system. However, it is clear that in this case, the gain of temperature will be lower than in the first case because we will have some heat loss. Now, the third type is a so-called dual system, where where we have two systems that are coupled, and the evaporator of the first system will be utilized as a tool to cool the condenser of the second system. So we can find some papers on this type of heat recovery. However, it is applied in some specific situation where we need two systems, and it is not generalized as the two previous concepts. Now, to present applications on these systems, we choose two different applications to show how generally we can do a heat recovery study. So the two applications are done by the authors, by me and my colleague, Dr. Mahmoud. So the first one is to show how we can do an experimental study of heat recovery system. The second one is to do a numerical study, and we'll see the advantage of every approach. So the idea of the first application, which is an experimental application, is to take a split system and to apply the immersed heat recovery concept. So to do that, we need of course a water tank in which we'll immerse our condenser. Now, the testing, of course, is done. Several experiments were done. Here I present one experiment. So the time of the experiment is almost 2 hours. The initial temperature of the water is almost 23 degrees. And the increase of temperature is almost 40 degrees. So we reach almost 62, 63 degrees. Of course, at the same time, we were seeing if the HVAC system is working well. So as we can see in blue, the curve that represents the temperature of the room, just to be sure that the heat recovery system is not affecting negatively the HVAC system. So as conclusion for this concept, this concept may be an excellent opportunity. 40 degrees is almost the range of temperature we need to supply hot water to a house, for example. The second application is on air-to-water heat recovery. Donc here we developed a code which is a bit like the code that was presented by Dr. Mahmoud. So the idea here is to use a numerical code which will allow us to do larger parametric study and to test a lot of configuration, a lot of parameters, and to change the configuration as we want, and to change, of course, the parameter of the HVAC and of the heat exchanger. So mainly it is based on the balance equation at the HVAC system and the balance equation at the condenser. The third equation is the balance equation at the heat exchanger. So finally, these equations will allow us to get the outlet water temperature of the system. So here I present the algorithm briefly. So of course we have a part of where we have the input. We will collect the different input parameters of the heat exchanger, of the fluids, and of the HVAC system. We will solve the energy balance equation at the condenser side, which will allow us to get the air temperature, the hot air temperature. Then, using the hot air temperature, we will solve the balance equation at the heat exchanger side, which will allow us to get the outlet water temperature. Of course, in this case, we will use an iterative method, so we will test we will do iterations until convergence. If we converge, we get the results. Otherwise, we will do a new increment to the application till the calculation till the convergence. So we choose to put the algorithm just to show the strong point, let's say, of the numerical approach, which is that we can do many calculations and we can test many parameters. Now I will show two different results. The first one is the outlet temperature, the water outlet temperature in terms of the water flow rate. And as you can see, the water temperature decreases with the flow rate, water flow rate. On the other hand, we can see that we have the curves for different systems, 1 ton refrigerant, 10 and 18 ton refrigerant. And we can see that when we increase the number of ton refrigerant, we get higher water temperature. The third conclusion is that we have some variation of the temperature, which is not necessarily expected, and which is due to the change in the flow rate nature, in the flow nature from laminar to turbulent. Another type of study may be done is on the diameter ratio. So the diameter ratio in this case, since we have a concentric tube, is the radius of the internal on the inner on the outer radius. So we can see that we have three different curves. The first one for the ratio of 0.25, 0.5, and 0.75. And of course, we can see that the outlet temperature increase with the diameter ratio, and we have the same conclusion as in the previous graph. The temperature decreases with the water flow rate. So finally, this is the objective of this work is to show or to present several types of heat recovery systems applied to the HVAC systems. Of course, we can find other types of heat recovery systems to be studied. So this is in the perspective of this work. So the first conclusion is that heat recovery is an efficient solution to face the energy crisis. We show several types of heat recovery systems applied on HVAC system. This can be done by several approaches, such as experimental or numerical approach. So we have several perspectives to carry out more experimental results, to develop other types of heat recovery systems, and to do a comparison between numerical and experimental study. Thank you for your
So, we have time for questions or comments. Yes, please.
Have you studied the effect of water temperature on the power consumption of the HVAC system?
On the consumption, you mean in terms of electricity?
Yeah.
No. We study the effect of the water temperature to the what we can obtain in terms of hot water temperature, but the energy consumption is not as it is in the perspective, of course.
In the case of the university system,
Yes,
you need a continuous flow of water. It's not just inverse.
of course.
Right.
Yes.
How does that affect the energy saving? Because you might need a pump for pump the water, and you need flow of water, so you're using water.
Now, of course, this, to answer you an accurate answer, I need to do of course, the study and do the comparison. But what I can say that if we want to install this, the idea of the system is to be installed, for example, for let's say daily utilization. So if I want to install this system in my house, of course, I will not have a continuous flow. I will have a flow to a certain time where I can store a quantity of water, and then this will stop.
I noticed that during 2 hours,
Yes.
you got the water to 60 degrees.
Yes, almost.
So
60.
say you're using the conditioning at night in Beirut, what will happen? At night during 10 hours, for example. Water will boil.
Of course.
You have no consumption, everybody is sleeping.
Yes, the question is, okay, the answer is that we need to do, I didn't present that, we need to put a control system. So in the experimental study, the idea was to study it, but we need to, of course, to make a control system. So we developed another experimental setup where we have a controller that may order the fan to be activated and to stop the in certain configuration to stop the cycling of water. So we can, let's say, we can couple the two systems so that we have the fan at the part of the condenser or before the condenser, and then the part that is immersed in the water. So the cycling will be until certain criteria that will be controlled by the control system.
During this experiment, what was the outdoor temperature?
The outdoor temperature. No, it's not. I think it was almost
30 and 35.
30. I think something like that.
Summer between
I
30
think
and
it was
35 degrees. But, excuse me, we don't have temperature limits problems because condenser does not exceed 100 degrees Celsius to boil the water. At the same time, water we don't need necessarily water to be flowing. We can have water at rest.
If it's a stagnant water and you don't have flow, eventually water will go. You have to keep pumping.
No, it depends on
Second law of thermodynamics, it depends on the temperature limits. If the condenser does not exceed 100 degrees, we don't have energy transfer. So we have to control. But at the same time, if we look from an energy point of view, we have done another study where water at rest may be more efficient than water flow, which is unobvious.
In heat transfer?
Yes.
Now, here it's important to say that the system also will depend on the capacity of the refrigerant in the HVAC system. So if we have a 1 ton refrigerant, it's not the same as, for example, 10 ton refrigerant. So the temperature of the condenser will depend.
The water temperature and the quantity of water.
Yes.
Of course. Thank you.
Well, question or comment? Yes, please.
As I find that this system might be applicable using domestic use in summer not only. Because in winter, the refrigeration condensing, the temperature of refrigeration will be low, and the temperature of the condensing temperature for the refrigerant itself not exceed the 30 degrees. So you couldn't achieve the specific temperature for the hot water supply temperature, it's almost 40 degrees.
Well, the answer is, of course, it is not the same if we are in summer. In summer, it's more efficiency in the system, of course. However, in some applications where in some applications maybe we will have a high temperature, say the HVAC system for some industries or some very specific system, we may have, even in winter, a environment that is approaching the summer environment. But in general, of course, this system is more dedicated to summer applications.
Okay, you want to comment? So, thank you very much. Now, I will give the floor to Marcel Arsenier, who is a senior mechanical engineer at Dar Al-Handasa Shell and partner Beirut Design Office. So, I'm sorry if the name is not well pronounced, but you are acting as a group leader for design team. I'm sorry, also, you're right. I'm sorry, I have to write paper. So, your paper will be presented, will be fresh air cooling plant in hot and humid climate comparative study. So,
thank you. This presentation is about a study that we made in order to compare different systems, in order to choose the best system, in order to provide cool, fresh air for a project in a hot and humid climate. The project was in Qatar, and the outdoor conditions was highly humid and very hot. Fresh air cooling load is constituting about 50% of the cooling load in hot and humid climates, especially if the building is well insulated. The fresh air always need to be dehumidified and cooled before being introduced into the space. Fresh air is required inside the buildings in order to provide a good indoor environment quality and to provide infiltration, to prevent infiltration from the outside, and to provide a make-up air for the exhaust system. The fresh air needs to be cooled and humidified before being introduced into the system, into the building. The outdoor fresh air will become a huge challenge, especially in green buildings, where in green buildings you are required to increase the amount of fresh air being introduced to provide better indoor environmental air quality. At the same time, you are required to decrease the amount of energy used to cool for the building. That's why cooling the fresh air becomes a challenging system especially for large projects where a large amount of fresh air is needed to be introduced into the system. So the aim of this paper is to compare 4 different configurations that was in order to decide which one to use based on the configurations were chosen based on the available requirements in the project. The outdoor conditions were chosen for Doha, Qatar, which are 46 degrees C as dry bulb and 31 degrees C as a wet bulb. This has a humidity ratio of 22.2 gram per kilogram. The living condition from the air handling units was required was 18 degrees Celsius and a water content of 9.5 gram per kilogram. The 9.5 gram per kilogram were chosen to simulate indoor condition, that is 24 degrees C and 50% relative humidity. Introducing the fresh air at this humidity ratio will not introduce any additional load on the HVAC system that is providing cooling for the spaces. The tools that were used for this simulation were the HAB software, ASHRAE psychometric analysis to draw the charts, and some energy conservation selection for the wheels used. The 4 different configurations were used. The first configuration is the most basic configuration that is used to cool and dehumidify air. And it is used as the baseline against which the other systems are compared. In the first arrangement, we have cooling the air to a lower temperature, where you have the humidity condensating on the cooling coil, and then using a reheating coil in order to heat the temperature up back to a higher temperature. The first configuration tested, we cooled the air to 14.4 degrees C, and then it was reheated to 18 degrees Celsius to meet the conditions that were required. This configuration consumes a lot of energy, since you are cooling to a very lower temperature and then you are heating back up to the... This is the basic system that is used for dehumidification. And this is the psychometric chart where you have at point 1 the outdoor air. It is directly cooled to point 2, where you leave the coil at 14.5 and about 90% relative humidity, and then you introduce heat between point 2 and point 3 to reach the conditions that were set initially. The second arrangement that we took a bypass of a small amount of air, and we didn't pass it through the cooling coil. And then after the cooling coil, we mixed the bypassed air and the air that was cooled by the cooling coil. We tried different configuration for the percentage of air that was bypassed and that passed through the coil. And we ended with the best configuration was that to cool the air to 10 degrees C using the cooling coil, and bypassing the 13.5% of the outdoor air. We are using the outdoor air to cool to reheat as a source of reheat. Even with this, we needed to keep the reheat coil in the system to raise it back to 18 degrees C. And this is the second arrangement where you have between point 1 is being cooled to point 2. You have mixing between point 2 and point 1 to reach point 3. And at point 3, you are also reheating to go from 3 to 4. 4 is the 18 degrees C and 9.5 gram per kilogram. In the third arrangement, we used a horseshoe configuration heat pipe, where you have a coil installed before the cooling coil and another coil installed after the cooling coil. These two coils are connected and you have refrigerant flowing between the two coils, where you pass the outdoor air through the first cooling coil, where refrigerant gets heated, and then at the same time the outdoor air gets cooled, and then the heat is transferred through the refrigerant to the second coil, where after cooling the main air stream using the cooling coil, you use this heat to heat back the air stream to the 18 degrees C. In this configuration, you don't need a heating coil, and you can rely solely on this horseshoe arrangement. And we needed to cool the air to 14 degrees Celsius, and this makes a saving in the reheat coil. And also saving in the cooling because you lowered the temperature before the coil. And this is the psychometric chart for this configuration, where you have between points 1 and 2, you have the first coil where the outdoor air is the temperature of the outdoor air is dropped sensibly, and then this heat is transferred back to between points 4 and 5 to reheat, point 3 and 4 to reheat the main air stream, and you have cooling between points 2 and points 3. In the fourth arrangement, we used a recovery wheel and the bypass from the previous arrangement. The recovery wheel is consists of a wheel that rotates, and you have one airstream passing from one side and the other airstream from the other side. And exchange of heat and enthalpy can occur between the two airstreams. For this configuration, we introduced outdoor air, and then we took a bypass from this outdoor air. This bypass, we passed it through a enthalpy wheel, where there was an exchange with an exhaust airstream. About 40% the exhaust airstream was. And then we mixed the output of the cooling coil that was cooled, we cooled the air to 10 degrees C with the output of the heat recovery wheel. Even in this configuration, we needed some reheat and to reach the 18 degrees Celsius. We tried different configurations, and the one that gave best results was to pass about 68% of the air through the recovery wheel. Definitely this depends on the amount of exhaust available, and to make this exchange between the bypass and the between the airstream and the exhaust airstream. And this is the psychometric of the process, where you have between point 1 is the outdoor, it's being cooled point 2 through the cooling coil, while between point 1 and point 3 you have the exchange at the enthalpy wheel that is both sensible and latent. And then point 3 and point 2 are mixed to reach point 4, and here we use the reheat coil to raise the temperature from point 4 to point 5. Here the temperature rise is smaller than was required, that's why the reheat coil amount gets lower. The results for these configurations are summarized in the table below, where you have here arrangement 1, it's the standard arrangement, where you need about 12,891 kilowatt of cooling and 713 kilowatt of reheating. The reheat can be done through electric, water, or arrangement 2, the one that we had a bypass coil. It turned out that to be not effective, since some of the latent heat are being bypassed through the coil, and also we needed more energy to cool to reheat. So the second arrangement was not efficient at all. The third arrangement, the one using the horseshoe, the cooling load was decreased by about 6.7%, while the heat recovery was zero, the heat was zero, so no heat was required. That's why a saving of 100% in the reheat and the 6.7% in the cooling was obtained. And for the fourth arrangement, the one using the horseshoe, using the recovery wheel, the initial cooling coil load was decreased due to the exchange with the exhaust airstream, so there was a 22.7% energy saving. And the reheat through the mixing that also decreased from 713 to 183 kilowatt. That's about 80.6 kilowatt of reheat saving. So the fourth arrangement proved to be the most efficient one among these four arrangements, and with a saving of 22.7%, knowing that the fresh air system can have fresh air cooling as about 50% of the total building cooling coil, that is a very considerable saving. Also, the reheat coil saving of 80.6% is also a very big saving. So the main objective of the paper was to find the best system among these three, and the fourth one proves to be the most efficient one among these systems. Thank you. Questions?
Please, you have questions.
How did you calculate the heat transfer through the energy wheel or the thermal?
We used a software from one of the companies.
Have you considered the RPM of the energy wheel?
We did a selection. We did a selection from one of the companies. We have the flows. We did a selection, and then we obtained the data. So you can't explicitly name fuel effect.
Do you consider the additional value from the fans for this bypass here? Because it will affect
It will increase, but yes, man, this is a point that was not addressed here, that this heat from the fan can be used for the heat. That's why this will be a positive at some point here, because the heat that you have, you can use it for the heat. For the fourth system, the additional reheat that you need can come from the fan. But this needs a bit further investigation to see if this heat is enough or you still need.
Could you please come back to the arrangement for your
Yes. Yes.
This arrangement in practical maybe reaching because here the thermal wheel is
Yes.
in parallel with the cooling coil, not in series.
Yes, these systems were done for a large project, and such system can, for this large project, it was feasible to go for such a system. It was not for a small-scale project.
Thank you for your presentation. I was just wondering, what's the main difference between an enthalpy wheel and an energy wheel? And how sustainable is such a configuration in terms of efficiency and running cost?
The energy wheel and the energy wheel transfers only sensible heat, while the enthalpy wheel transfers both sensible and latent heat. It has a material that can absorb heat, humidity from one side and dissipate it to the other side. Can you the other question?
In terms of running costs, how sustainable is using such a configuration or such an arrangement?
These configurations are used, and you have enthalpy wheels applied. You are changing the configuration. Here you have the savings in the end. Here you have a saving of 22%, 0.7%, and a saving of 80.6% compared to the traditional system that is arrangement one. And in the end, you need to provide a dehumidified and cooled air. So you are always comparing to the base case, the traditional system. And here you are making a better system. This is the.
So in terms of running cost, is there a high or low running cost?
No, the running cost, here, Mr. The fourth arrangement, you are adding a heat wheel, the recovery wheel. It has a small motor to rotate it. You have some at static pressure, but as I told him, this you can use it for reheat. And you can use it, this heat that adds in the static pressure, you can use it to reheat and remove this heating coil, for example.
It is not. It is a significant bypass where you mentioned that 68% of the air to bypass
through the cooling coil. You have 23%. No, you have 23% passing through the recovery coil. No, the total amount of air is still the same here. The whole system has the same amount of air passing through.
Okay, right. For the traditional system,
yes.
Suppose we have the 1,000 CFM, right?
Okay.
Okay. And the proposal
it's also 1,000 CFM.
I understand I need to bring this 1,000 CFM from the outdoor condition to specific indoor condition, right?
Yes.
Right. Now, as I understand from this arrangement that you need the 68% additional air.
No. We don't need anything. We're just bypassing an amount of this fresh air. In all the systems, we are using the same amount of total air.
You take 68% of the
yes.
the fire airflow.
Yes, we have 68% through the coil, and we have 23% through the recovery wheel. It's not additional. There is no additional air introduced. We are just benefiting from the initial high temperatures of the fresh air to do some sort of reheat after the coil.
But in this scenario, you only cool the rest of this percentage is a cooling coil.
Yes, the other percent, here we cooled to 10.5 degrees C. And then after the mixing, we went back up. And that's, we cooled down, we removed a lot of amount of humidity condensed on the coil, and then we mixed the two streams to raise it up back to the temperature. You can see this on the symmetric chart here. Here we cooled down to 0.2, and at 0.2 then we did the mixing to go back up to 0.4. While in the traditional system, you have everything cooled to 14.4 degrees C. That's at a higher temperature. So we use the initial hot air to reheat the air that was cooled through the cooling coil. Here you can see we cooled from 1 to 2, and then we mixed 0.3 and 0.2 to reach 0.4.
Okay.
First of all, thank you.
Thank you.
Second, have you made some elaboration regarding the budget of the system, arrangement 4, especially regarding the return on investment, regarding the initial cost? Any
The
values?
study was concerned with the heat amount for this system.
Yes, but no values regarding the budget prices or the system and the return on investment, initial cost, something like that?
Definitely it will cost more on the initial investment.
Yes.
The running cost depends how you are doing the reheat. If you have if you are doing the electric reheat, it will definitely be. If you are doing or a boil, if you have the reheat generated by some green source, or it will differ. Yani this paper concentrates on the part of the energy from this system. The whole study has many variables, to see how this system fits into a global study for a project.
Thank you.
We have sometimes more, so if you have also other comments or questions more generally for the three presentations, because we have some time, so if you have some comments.
I try to understand in the psychometric. From point 1 to point 2, this is the portion of the air passed through the cooling coil, right?
68%. Yes.
No. This is not 60.
68% air passes through the cooling coil.
Right, 68% for the percentage through the cooling coil. The bypass is the 32, right?
Was okay with the three presentations? No. So, in that case, we will end the session. You will have more time before the dinner, and of course, I think that you have some indications regarding the dinner at Felix Hotel, I think. Okay? So, thank you very much, and thank you to all the presenters.